All right, we're going to take a quick review of the kinematic equations that we learned in grade 11 as part of our unit, which we now are going to call mechanics. So mechanics is a combination of both kinematics, which is the measurement or the description of how things move. And of course, we describe this by using things like displacement or position, right? Velocity or speed, and acceleration, of course. And the critically important thing is how each of these changes with time. So time is always an element. And we talk about how displacement is velocity is the rate at which displacement changes, and acceleration is the rate at which velocity changes. So that was kinematics. And then you combine that with the dynamics, which is makes things move, and that gets us into the whole world of Newton's laws and forces, net forces, and all of the things that go along with that. And that together makes up the entire sort of concept or unit of what we call mechanics. So first, what we're going to do is we're going to take a few minutes to just kind of bring all this part back, and then we'll talk about the dynamic part of it later. So kinematics. So you'll recall, just very quickly, that if we take a person or something that moves, I'll just use a person, and we say that they slide around here, let's say they walk or they run, and they move 6 meters, well, we can describe that as a displacement or a change in their position, right? This is a change in position. And of course, remember that we usually include directions when we're talking about kinematics. So these are vector quantities. They have both magnitude, the 6, but also a direction. So this direction could be to the right. Change in position, let's spell position right. That's a change in your position, which is what we call displacement. So displacement is sort of a measurement of that change in your position, measured as the difference between your starting point and your ending point. And remember that it's a direct measurement. Okay, so then we have the concept of time. Well, obviously it takes a certain amount of time to make this happen. And so what we can do is we can describe a comparison between the change in position, right? And the way we say compared to in math language is by a fraction, by division. Change in position compared to the change in time. And when we do this little sort of comparison, right, we get a new concept. The change in your position compared to time is what we call our velocity or speed, how fast we're going. If you change your position in a very short time, you do it very quickly. If you change it in a very long time, you do it very slowly. And so this, of course, represents the quantity we call velocity. And so we write this as a mathematical expression, the change in displacement or position over time. Now, when you get on in math, they often will use an S for changes of position. So they'll write delta S over delta T. And the reason for that, I think, is because the D, if some of you have taken calculus, you know that the D is heavily used in the derivative notation and so on. And so we don't want to get too confused. So they use an S a lot in the mathematical models. And many of your professors, if you go on in university, you might find them using an S instead, or sometimes even just an X, which is a little confusing because it doesn't have to be on the X-axis, right? It could be any movement. But anyway, just so you know, be aware that sometimes when you go away to school, the teacher is saying the exact same thing as your high school teacher, but the professor is using different notations and it just looks like something completely different, and it's not. So they sometimes will see an S. And that, of course, is an equation that we recognize when we draw a graph. if we draw a displacement in time graph, we recall that take any line here, there's an initial D, a D1 right here, and then there's another D sort of up here, which is the second displacement, the second position. And the displacement would be the blue line that travels between the two positions. But of course, we also have an initial time value of T1, and there would be a second time, right over here, of T2. And so what we could do then is we could say, okay, let's compare on this graph. Remember that the slope of a line is equal to delta y over delta x. Well, that's when you're using x and y as your axes with no context. We have context. Our y is a d, and our x is a t. So our slope is equal to delta d over delta t. Well, that is exactly a comparison of the change in position compared to the change in time. We call this the rate of change. That's an important word. Whenever you compare something to time, this is the rate of change in position. That's what velocity is technically. It's the rate of change of position. Okay? And some of you know about rates of change from calculus if you've had it. Okay. So now we have the rate of change of position, which is the slope of this line. Well, that means that the slope of this line must be the velocity at which the object is traveling. So the slope on the displacement time graph tells us the velocity because it represents the rate of change of position. And we can figure that out. If we look at this graph, we can see on the top I have, or actually not on the top, over here on the side, right here, that value is equal to D2 take away D1. That's how you would figure that out. Right? If D1 was 2 and D2 was a 6, well, you'd know it would be 4 in between them because 6 minus 2 is 4. And then, of course, down here we have the T2 minus T1. So we can take the equation for velocity being the rate of change of displacement compared to time. And then we can write D2 minus D1 divided by T2 minus T1. And remember, there's a bit of a shortcut we could use. It's kind of a cheap little way of writing it. It's more like a slang version of this. But if we envision that D1 is a 0 and T1 is a 0, which often is the case, then this sort of reduces to the D2, which is essentially just how far you've gone, and the time taken, which would be T2 or T. And then we can multiply both sides by T and get D equals VT, which is sort of the way we sometimes describe this little scenario. But it's important to remember that this is the real equation, because there's no guarantee that D1 or T1 has to be a 0. In many of the scenarios that we study, it is, and this makes sense. But it doesn't have to be, so you have to be careful of realizing the limitations when you're using this little slang equation, because it does have some issues if you're not starting at zeros. Okay, so that was how we described the rate of change of position. How fast your position changes is called your velocity, and it's equal to the slope on the dt graph. Well, then we imagined if you were going along. Let me go back to that for a second. What you'll notice is no matter where you go on this little blue line, if I start here or here, if I pick any point, all these points I'm drawing in black, they're all equal to the same slope. The slope never changes. And we call this a constant speed situation. So that describes moving at the same speed the entire time. But it is possible, of course, to change your speed. You could start by moving very slowly and then go faster and faster and faster and faster. So that down here, this end, you're moving at a faster speed. And here you're moving at a slower speed. So what's interesting is now the speed has changed. So now we're talking about a change in the velocity. And of course, it takes time to change your velocity. So we could compare the change in velocity to the change in time and get what we would call the rate of change. Remember, when you compare anything to time, it's called a rate. So the rate of change in velocity. And what is that? Well, that's speeding up and slowing down, right? How fast you change your speed is called your acceleration. So now we have a way to describe this acceleration idea, rate of change in velocity. So we write something like this. And of course, by the same mathematics as before, if I draw a graph and I draw a velocity time graph, I can take something that has any two velocities, a v1 and a v2, and I can take a t1 and a t2, two times. And of course, we can draw a line that represents the changing v and the changing t. So we have this, which is my t change, and this, which is my v change. And so that's my delta v, and this is my delta t. And the slope is equal to this. And so the slope on this graph gives us the acceleration. It's the same mathematics as the previous thing. It's just that we're using a velocity time graph instead of a displacement time graph. Okay? So what's interesting is that acceleration, let me get a thinner line here. Acceleration is the rate of change of the rate of change of position. Because this is what we call velocity. So acceleration is the rate of change of velocity, but it's the rate of change of the rate of change of position. Now, some of you may have taken calculus already, and so you know that calculating slopes on a nice, easy line like this is very easy. We can do it with these equations, but what happens when you have a situation that looks something like this? And so in order to take the slope at a particular point, you have to have developed the art of calculus. And by taking the derivative, we say dy by dx, which in our case, if we're using this is why we like to use s, you see, because it's dd. This would be dd by dt if we described a derivative on this graph. So let's call this s, so we get the s right. So in math, ds by dt, well, that represents the rate of change of position. And that's what we call velocity. So the velocity is the first derivative of position. And for those of you who know, if you take the derivative of a derivative, you get the double derivative, right? Which would be ds squared by, oops, I got it backwards. Let me just erase that. Went too fast there. D squared s by dt squared, which is like the derivative of the derivative. So it's the rate of change of the rate of change of position, right? And so you can see how these notations mean the same sorts of things as these slope equations. It's just that we're using slopes on very easy graphs that are all nice straight lines or simple curves. Whereas in calculus, you can do the same procedure with the graph of anything by this idea of the derivative. And so you would have learned that in your calculus class. And so that's how we get our first two major sort of equations that we use in kinematics. So we say that v is equal to delta v, the change in position over time. And we say that a is equal to the change in velocity over the change in time, right? Or if you wanted to use more complex calculus, you would say that v is equal to ds by dt, the rate of change of velocity. And you would say that a is equal to dv by dt, the rate of change of velocity, which is the same as saying d squared s by dt squared. Don't worry about this side if you haven't taken calculus yet. I like to tie it in because calculus is the language of physics. And in your first year of university, you'll begin to use your calculus when you're describing physics. So it's a good idea to sort of start to see how they're the same. And you should remember that when you learned about the derivative, it was all about calculating the slopes of lines, which is what these are. So these are sort of baby steps towards this, which is describing the slopes on any possible situation, moving in any kind of possible way. And so that's how we get our two equations, what I call the slope equations that describe velocity and acceleration. Now, acceleration is a little bit tricky in terms of how we assign direction, as well as deal with the speeding up, slowing down part, but we'll discuss that in a different video. Now, the other thing that can be done with graphs is the idea of area. And if you took calculus again, in AP calculus anyway, you learned about integration, which is how we calculate area. We don't have to know that. We're just going to do the simple stuff, right? We're going to keep it easy. So we can use squares and triangles and rectangles instead of trying to figure out the area of a rattlesnake or of a cowboy hat or something. That's just too complex. So let's take a look at what happens when we draw a DT graph and we take some object. Let's say it starts here and it moves to here. Okay, actually, I'm sorry, I want to draw a VT graph, a velocity and time graph. My mistake. So this blue represents the initial velocity that something is moving at, v1. Whoops, I wanted that to be blue. Sometimes it doesn't listen to me. And this would be our v2. So we've changed speeds. And of course, in doing so, we've also changed times. So we have a t1, and we'll go over here and draw a t2. And I'll draw the line in purple going from here to here. So here's what we have. We have a line. We could calculate the slope of the line to find the acceleration. But what I want to do is I want to figure out what the area of this line would be. So I draw this line here just to show the end, ends at T2. What I have are two regions. If I cut this area, the area is always measured between the graph and the horizontal axis, the t-axis in this case. What you can see is, if I shade in with a crayon here, what I have is a red version, or a red area, which is this triangle up on top, and I have a blue version, which is this here. So how can I calculate the area of this particular graph? Well, before I jump into that, why would I want to calculate the area of this particular graph? What would be the point of that, right? Why would we want to bother? Well, let's look at a simpler graph for a second, just to see how this concept might play out. Go back to my pen. Let's look at a simpler graph like this, and let's take something that's moving at the constant speed of v, and it's going like this, never changing. Okay, and let's say I calculate this time t, and we go that far. Well, what's happened in that time is, well, what would the area be? Think about that. If I color in the area, it's this blue box, right? There's the area between the green line and the axis. Well, if you think about it, the area is just the length times the width. Well, here's sort of the width, and that's v, and here is the length, which is t. So the area on this graph, area, is equal to length times width for a simple rectangle, which is v times t. Well, guess what? V times t is equal to d. We know that from before. The displacement is speed times time. That's the sort of slang version of the slope equation that we use to describe velocity. And so that means that area corresponds to displacement. So knowing that, we could calculate the area now under this more complicated situation that I've drawn on the other side, and know that it's going to give me some indication of the displacement of the object. So let's continue where we were. Well, we would have area equals length times width for the rectangle, the blue part, plus 1/2 base times height for the red part. Those are the triangles area, right? So let's go through that and see what we can figure out. Well, the area will become the D. We know that from what I just showed you. The length and the width of the blue triangle, I'll draw these in blue so we can color code it. Well, here is how high that rectangle is, the blue rectangle. It's V1 high. So V1, and its length is here, which is T. T2, but really it's just the time that has elapsed. So V1T, right? If we wanted to be very, very specific about it, it's the change in the time. So we would write V1 delta T to be a little more precise, okay? But then we would have to add the triangle. Now this is a little bit trickier in red here. This is the height of the triangle. How do I get that? Well, if I look over here, I have a V1 and a V2. So this height would be V2 minus V1, right? Whatever those numbers were. Here, this red line I'm drawing represents V2. And then if you just take a little eraser and subtract V1, you end up with V2. So, put that back. Let's call that's the height. And then what's the base? Well, the base is, again, the T. So what I get over here for the red part is 1/2 of the base, which is V2 minus V1, and then this would be T. Now, technically, it's delta T. Remember how we sort of said we could take the shortcut. We could take the shortcut of imagining that T1 is a 0. So T2 is really the same as delta T, and we just call it T. It's kind of a little bit simpler. But technically, this would be times delta T. So this is how it's more precisely written. But a lot of textbooks just write it the other way. Now we can change this a bit. I'm going to take the top one, and I'm going to go change it a little bit. So take this equation up here. In fact, I'll just start it again. D equals V1T plus 1/2 of V2 minus V1 multiplied by T. Now, what happens is, if we remember from our slope equation, A is equal to delta V over delta T, right? And so A is equal to V2 minus V1, and T, we could just, since we're just using T here, see, we're using T to represent delta T, we'll just use it over here as well. And look what happens. The quantity of A multiplied by T is equal to V1 minus V2. You multiply both sides by T, and you get here, which means the V2 minus V1 on this side over here can be replaced with AT. We can do a substitution. And we get D1T plus 1/2 AT instead of V2 minus V1, because they are exactly the same thing. And that leads us then to V1T plus 1/2 AT squared, right? Or more precisely, D equals V1 delta T plus 1/2 A delta T squared. It's a little more cumbersome when you put the delta in there. So if you just remember that these T's that we're using represent the total change in time, delta T is the same thing. If T1 is a 0, of course, which it almost always is. So this gives us yet another equation that we can add to our bank. We now have 3 ways to sort of model and describe motion in our kinematics so far. Okay, one more thing we can do is create a new equation. This is an area equation that we've just done. You might ask, well, what if you do the area equation on the dt graph? Well, it turns out, right, that if you did try that, so let's say it's a dt graph, and you have something here that's going along like this, what would it give us? Well, the area of this would be the change in the d multiplied by, right, so just the d, let's just call it the d, multiplied by the time. This distance over here is the time. So distance multiplied by time. Well, that doesn't really give us anything useful. There's nothing that we have or that we are interested in knowing that can be found by multiplying distance and time. Velocity times time is useful to get displacement, but there's nothing or no place where this is going to give us. So although we can mathematically do it, it doesn't really help us, and we don't derive an equation for it because there's nothing really to be solved by doing the area on a dt graph. So there's only one area equation, and that is this one on the vt graph. I suppose we could also do areas on AT graphs, and it'd be interesting to see what they would produce, but those aren't part of the standard kinematic equations, so we won't worry about that. Okay, so slopes and areas. The last equation is neither a slope nor an area. What it is it's basically just a converging of two of the formulas we already know. And the reason for doing this is so that we can have a tool or a model that does not rely on time. We want to basically take the t's out of the picture because there might be a situation where you don't know what t is. So we're going to start with this equation, v1t plus 1/2 of at squared. And then we're going to do something interesting. We're going to take this equation that we also know is true, v2 minus v1 over t. Remember, that's the slang version of delta v over delta t. I'm just not using the deltas just to keep it a little bit simpler looking. Now, instead of writing it this way, I'm going to isolate for t. So I multiply both sides by t first. And then I divide both sides by a. And I have this interesting little version. This tells me that whatever t is, this junk on this side, v2 minus v1 over a, is exactly the same thing. So what I can do is I can substitute this into this other equation wherever I see a t. And that creates a very complicated looking equation over here. v1 multiplied by v2 minus v1 over a instead of the t, plus 1/2 of a multiplied by v2 minus v1 over a squared. Now that looks kind of messy, but there's going to be some cleanup here we can do using some simplifying techniques of mathematics. So the first thing I will do is I will multiply this v1 into the brackets to sort of get that out of the way. So that would give us d equals v1 times v2 minus v1 times v1, which is v1 squared. And then there's still an a on the bottom. The next thing I can do is sort of clean up the mess over here. But before I do that, I better square this top and, of course, square the bottom of this fraction. So I'll do that next. I'll square that. So I'll write plus 1/2 a. I won't touch that yet. But the top half of that, remember when you square a binomial, v2 minus 2 v1 times v2 plus v1 squared. If you can't remember how to do that, then just do this. There's the square, right, of that binomial. Multiply these, multiply those. Remember FOIL, right? That's how we did that. So we get that on top. And on the bottom, we have a squared. Okay, now what I can do here is a little bit more, a simplification. I can take the 2 and multiply it into the brackets on the bottom, and the 1 multiplied into the top. And then I realize if I divide top and bottom by a, then this is on the top, that'll disappear, and this will become just a. So it's like you're canceling an a, you know. I don't like to say cancel because you're not canceling anything. I just divided top and bottom of this fraction by a. which is a rule that's allowed. Do the same thing to the top and the bottom. So that gives us this. V1, V2 minus V1 squared divided by A plus the 1 on the top won't change anything, so the top will just remain where it was as such. The bottom, however, will get a 2 multiplied into it, and there is an A left over, so now I get to here. And now I have a slightly better situation, but still fairly complex. We can simplify these fractions in a number of ways. A lot of students want to jump to the common denominator, but there's one way you can clear denominators, and that is by multiplying by sort of the largest one. So if we multiply the entire equation by 2a, watch what happens. We get a mysterious line, apparently, out of nowhere. But if we do that math, multiply 2a times the entire equation, 2a times this side would be 2a times d. Now watch what happens when you multiply 2a. I'm gonna write it down so you don't think I jumped any steps here. Let's write that. And 2a times this. I think I missed something here. Let me go back. Yep, I did. My mistake. This V2 is supposed to be V2 squared right there. I forgot the square and I didn't carry it through, and I noticed it now. Better late than never, right? V2 squared minus 2v1 V2 plus V1 squared. Make that correction so we don't end up in a mess when we get down to here. Okay. So then we have 2AD. Well, here, divide top and bottom by A and multiply the 2 into the brackets. 2 V1 V2 plus 2 V1 squared. Over here, divide top and bottom by 2A, and those disappear, and you just have V2 squared minus 2 V1 V2 plus V1 squared. I think I have another error. I'm just going to go double check what happened here. Yeah, see what I did? Oh, I've been going too fast. Unfortunately, this little guy down here, I made him a plus. I'm watching the clock here instead of watching what I'm doing. So this is also a good lesson in why you should never hurry through any kind of calculation. There's a minus there. Everybody see where I'll highlight it in red so you can see where I changed it. And I just turned it into a plus by going too fast. So now I think we're okay. Now we can look at some like terms, and we can see that the 2v1 v2 is positive here and it's negative over here, so it essentially subtracts to 0. And then we have 2ad, and we have negative 2v1 squareds and a v1 squared, which will leave us with a minus v1 squared and a v2 squared. So that's pretty simple when you do it right and don't make the mistakes that I made. It simplifies to something quite easy. And what we can do is rearrange this. We usually move this over to this side. So it's 2ad plus v1 squared equals v2 squared. And we just rearrange that, write it in the mirror, and we write it like this. And we get this equation, which you'll remember from last year, which is an equation that eliminates time. If you ever want to eliminate a variable and you have two equations, isolate for that variable, like we did way up here, isolate for time, and then substitute it, and the t disappears, see? And now we have this equation, which we can use whenever we want if we don't have any time information. It's quite helpful. So we have the following kinematic equations. We have so far V equals delta D over delta T, from which we get our common D equals VT equation. Then we have A equals delta V over delta T, the rate of change of velocity, which we get this equation from. sort of our slang version. And then we have the area equation. Now, what I didn't show you is there's another version of this. And if you go back very quickly, see this area we were figuring out here, right in here? There's another way to get this area. We could take the box in its entirety up here, the red box I just drew, and that would be V2 times T, length times width. This is V2 times T. And then we could subtract the blue triangle on top, which is exactly the same as the red triangle underneath. So there's a version of this where it's V2T, take away the 1/2 AT squared. So I'll write that in here as well. And you can go back and look at that later if you really want to see how that works. I've found over the years that I've never used this equation very often. But oops, minus. Boy, that's 3. That's strike 3. I guess I'm out for the day. Good thing we're almost finished. Minus. So they look very similar, but one has a V2 and a minus, and one has a V1 and a plus. And that can be used as well if you don't have information about your starting velocity. And then we have V2 squared equals V1 squared plus 2AD. These are considered to be the 5 standard kinematic equations that we use to describe all of the motions of things in relatively simplistic terms, right? If you want to describe things that are not nice straight lines or simple curves like parabolas and things, then you have to rewrite these in terms of the calculus versions of them and use these calculus derivative operations and integral operations. That's a little more complex. But these are the 5 equations that work for, well, you'd be surprised. They work for a lot of things. So they are quite useful, even though they do have some limitations. And then the next step, of course, is to practice using them in different scenarios, which is what we're going to do for the next little while. So we'll stop there. I'm sorry about the little errors. I hope you got those straightened out and you weren't too bothered by that. There's our kinematic equations.